Okay. I did just film this, but I apparently was cut off about a minute or two before the end, so I'm going to redo it. Moving on to the next problem, and this is one of my favorite problems, and I'll explain why in just a little bit. We have a cyclist generating 1,400 watts of power, moving at 18 meters per second. That's the average velocity. We want to know the force the cyclist is pedaling with, F. So we look at the equations that we have on the front. We notice that P equals F times average velocity. The power equals the force times the average velocity is one of them. So that's the equation we're going to go with. P equals F times average velocity. We plug in our values. 1,400 watts of power, 18 meters per second. Solve for F, and we end up with 77.78 newtons. Now, the reason that this is my favorite problem, or one of my favorite problems, is it is very, very similar to the problem that I got wrong when I took the physics Regents myself. I ended up with a 99 in the physics Regents. There was one question, and I knew exactly, when I found out my grade, I knew exactly the question that I had missed. There was only one question that I really wasn't sure about, and it was something similar to this. It was a cyclist question with were generating some power and they were moving at a certain speed at a constant velocity. And the question was, what force is the cyclist pedaling with? The reason I got it wrong is I started thinking, okay, well, this is the average velocity, and it seems like that's not changing. So if the velocity is not changing, there's no acceleration, and there should be no net force then. So I was like, how can there be no net force, yet I'm getting a value for a force here? The error with my thinking was that this is not the net force. This is simply the force that the cyclist is pedaling with. This is the force that they are exerting on the pedals. This isn't accounting for, let's say, like air resistance or friction from the bicycle itself or the road. This is very different. So when I had that question on the Regents, I went wrongly with saying that the cyclist was not exerting any force on the bicycle, and so I got it wrong. So I always like to point out this question, and I will point out that that exact question that I got wrong is on your power homework. So you'll be doing that very soon. If you get it right, you're officially smarter than I am. Okay? All right, second to last question. If a machine is rated for a power output of 210 watts, that's the power, how much time, T, would it take the machine to lift an object with a weight, remember, weight is a force, the force of gravity, of 30 newtons, a distance of 5 meters at a constant speed? I have P, I have D, I have F. I'm just looking for T. So the equation I'm going to use, P equals F over D times T. It's going to get set up like this. Be very careful when you set it up like this. 210 watts equals 30 times 5 over T. You can't just divide this 30 times 5 to the other side and call that your answer, because T is still on the bottom. We need T to be by itself and on the top of any particular fraction, or just not in the denominator. So what we should end up doing here instead is cross multiplying. That 200 watts is really over 1 if you think about it, so we can do 210 watts times T equals 1 times 30 times 50, which is 150. Then we see all we have to do is divide by 210 both sides, and we see that the answer is 0.71 seconds. That's the total time that it takes for the machine to lift this object. A little under a second. The last question is a graph question. The graph below shows the work done as a child pulls a wagon over a period of time. What is the average power that the child develops? So this is kind of an interesting graph. It's a work versus time graph. What this shows is the basically cumulative amount of work that the child has done over the course of the 10 seconds. As time goes on, he does more and more work. That doesn't mean he's trying harder and harder. It's just all that work is adding up. He is, at 10 seconds, he has transferred this much energy to the wagon. So we have a work versus time graph. Since this is a W versus T graph, and remember that P equals W over T, we also know that the slope of any graph is equal to the change of Y over X. But the Y variable in this case is work, which is W, the X variable is time, T. Look what we have. The slope is equal to the change in W over T. Well, W over T is equal to power. So it turns out that here the slope is equal to the power P that is generated. So all we need to do is find the slope of this. Slope is given by y2 minus y1 over x2 minus x1. Here are the points that I've picked. 0, 0, and 10 looks like about 700. I'm going to plug those in. I get 700 over 10, or the power is equal to 70 watts. All that means is that 70 joules per second were transferred from the child to the wagon. And if you look at about 1 second, Yeah, that's probably about 70 joules. 2 seconds, that's about 140 joules, and so on and so forth. So just remember that with a graph like this, work versus time, all you have to do if you want to find the power is find the slope. This is a constant slope. That means it's a constant amount of power. The rate of work being done over time is constant. It doesn't change. So that's it for power. It's a fairly straightforward topic. I might have a little something for you guys to do tomorrow, but I'll send it out over Remind. And by something, I mean in addition to the homework. I think I might be able to figure out a way to do something kind of interesting with this. So that's it for right now. Thanks for watching. And when we come back on Monday, I think what we're going to do is we're going to tentatively start kind of dipping our toe into the electricity units. We're going to start with static electricity, then we'll move on to circuits. So we're going to try to do that. I might have some neat demonstrations I can, do and show you. Until then, let me know if you have any questions. Stay healthy. See you guys later.